Okay, these are GCSE past paper questions. This is the second one from our rates of reaction series. Okay, let's have a look. Okay, Christina investigates the reaction between magnesium and hydrochloric acid. Magnesium chloride and hydrogen are made. Write down balanced symbol equation for this reaction. Okay, so what have they told us? They've told us our products and our reactants, okay? So our reactants are magnesium and hydrochloric acid. Our products are what is made, and they are magnesium chloride and hydrogen. So very quickly, you should be able to write down the word equation for that reaction. Now, the next step is to turn that into a symbol equation. And some of this is quite straightforward. There's one little tricky bit around the magnesium chloride that you should watch. Okay, so let's just replace each of these words with our symbols from the periodic table, using a bit of our experience as well. So magnesium is Mg, hydrochloric acid is HCl. That's knowledge which it's assumed that you've built up over sort of about 5 years of studying chemistry. It's one of those standard acids that you need to know the formula for. You should also know from your covalent bonding topic that hydrogen is a diatomic molecule and it exists as H2. The more tricky one to work out is magnesium chloride, because you're going to have to think about your ionic bonding. Okay, let's take a look at that one then. Now, we know that magnesium forms a 2+ ion. It loses 2 electrons to achieve its full outer shell. It's in group 2 and it forms a 2+ ion. We also know that chlorine, to achieve its full outer shell of electrons, it needs to gain 1 electron because it's in group 7. So if these two substances are going to react together, they need to accommodate this electron donation and receiving between them. So magnesium is going to donate 2. Chlorine, if it's one atom of chlorine, can only accommodate 1 of those electrons. So the ratio of those atoms together are going to be 1 magnesium atom for 2 chlorines, and that way the 2 electrons that are donated from the magnesium each get accommodated, 1 in each chlorine outer shell. Okay, that is covered in more detail in the ionic bonding topic. So that's our magnesium chloride, and that can just slot into our equation as it has done on the screen. Okay, now that gives us our symbol equation. If this is as far as you get in the exam, that's great. That's going to allow you to gain 1 mark of the 2 marks for a balanced symbol equation. So if you can't balance, don't panic. Just write this down and you will be eligible for 1 mark. But we're going to try and balance it. Okay, now when we balance equations, we have to look at the number of atoms of each substance on the left of the arrow, and then make sure that it's the same as the number of atoms of each substance on the right of the arrow. So we're just going to do a little tally here to see what we've got. Now on the left, we've got 1 magnesium, 1 hydrogen and 1 chlorine. On the right, we've got 1 magnesium, 2 hydrogens and 2 chlorines. So immediately you can see that we've got a discrepancy in our number of hydrogens, that's not balanced. Got a discrepancy in our number of chlorines, that's not balanced either. So what we're going to have to do is we're going to have to put some numbers into this equation to try and make that difference up. Now it's up to you whether you want to try looking at dealing with the hydrogens first or the chlorines. In this case, I am going to try and deal with the hydrogens. So what I need to do is add a number somewhere on the left hand side of the equation to make that number of hydrogen atoms equal to 2. And the way I'm going to do that is I'm going to put a big 2 in front of my hydrochloric acid. Okay, that means 2 molecules of hydrochloric acid are going to be involved with every 1 molecule of magnesium. Now let's do another tally, see how that's worked. Let's get rid of those 2 first. Now we've got magnesium is 1, hydrogen is 2 and chlorine is 2. On the right hand side we have magnesium 1, hydrogen 2 and chlorine 2. That's fantastic because it means we've actually, by dealing with the hydrogens, we've managed to sort out the chlorines as well, and we now have a balanced equation. All there is left to do is to write that equation down in our space provided. Here we go, magnesium plus hydrochloric acid is magnesium chloride plus hydrogen, okay, with all the correct numbers in there. Okay, let's see what the rest of the question needs us to do. Look at the diagram, okay? It shows the apparatus Christina uses. Now, you should be familiar with this sort of apparatus. You've used it a lot in the labs. We have a gas syringe, we have some hydrochloric acid in our conical flask, and we have some magnesium lump at the bottom of the acid in our conical flask. She measures the volume of gas in the syringe every 10 seconds. And she's given us a graph of her results. Let's have a look at this graph. Now, the x-axis of the graph shows us time in seconds, and the y-axis shows us the total volume of gas given off. So we can see that as the reaction progresses, more gas is given off until it sort of levels out when the reaction has finished. Okay, at what time did the reaction finish? So we're really interested in looking at this y-axis to see when no more gas was given off. And what we can do is you can mark a line on the graph, and you can see that it's about 56 seconds when that line has levelled off. In fact, let's put that in. If you look on the mark scheme, it allows us to have 54, anything between 54 and 58 seconds. So if you're a bit worried you haven't quite got the position correct, there's a little bit of tolerance there. Okay, next part. Calculate the rate of reaction for this reaction during the time interval from 0 to 20 seconds. So they've given us a specific part of the curve to look at. Well, it's a straight line part of the graph actually. From time equals 0 to time equals 20, I've marked it on red. Now, when we work out rates of reaction from graphs like this, we're trying to calculate the gradient, because that's going to give us the volume of gas given off per second, and that is the definition of your rate of reaction. So we're going to look at that red line, and we're going to look at the change in y. Okay, and that's going to be equivalent to 15 centimetre cubed. We're then going to look at the time interval that took, and of course that's 20 seconds because that's been defined for us in the question. And the way we calculate the rate of reaction is we divide 15 by 20. The answer to that is 0.75, and then what I need to do is put that in the space provided. Rate of reaction is 0.75 centimetres per second. Okay, right, let's move on to part 3. Christina repeats the experiment. This time she uses powdered magnesium. Key point there, powdered, it's in bold type. That's really important. You need to make sure you consider that in your answer. The reaction is much faster. Use ideas about the collision theory model to explain why. And there you go, that's your final clue, collision theory model. So that's really the ideas that you need to be including in your answer. Right, okay, now a collision between the reactants must happen if we're actually going to have the reaction proceed. Okay, so we need to make sure that our reactants meet each other. So I've drawn here our magnesium represented with the blue particle, and our hydrochloric acid represented with the red particle. Obviously hydrochloric acid is made up of 2 atoms, 1 hydrogen, 1 chlorine joined together, but just for the purposes of this model I've drawn them as one red sphere. Okay, right, now if the reaction is going to happen, those two have got to meet, they have got to collide, and that's what collision theory is all about. Now, if I take my lump of magnesium, now I've drawn this as a bit of a square. Obviously magnesium doesn't really look like that, but at least I can show you the effect of making some powder out of a lump if I use this shape. And if I consider a powder of magnesium, if you look at these two, they're actually the same quantity of magnesium. I've just broken it up into much smaller pieces. Now let's consider the original surface area of that magnesium. Okay, you can see that by breaking it up, we actually create a lot more surface area. So the surface area becomes a lot larger when the particle size of the magnesium becomes smaller. Now that's absolutely key. If we think about our hydrochloric acid molecules that are going to be floating around, they are going to need to collide with the magnesium. Now if I've exposed more surface area, it means that there's more chance of a collision happening. Just have a look at this. Once the particles can move about, they can get in and touch all this new area, and that means that there's a much greater chance of a collision happening, and therefore a much greater chance of a successful collision happening. And the result of that, of course, is that the rate of reaction increases. The reaction is a lot faster. So let's get these answers down in our question now. Okay, so powdered magnesium has a greater surface area than lump magnesium. That's going to be where our first mark comes from. So you've shown that you understand this relationship, that when the surface area is larger, it's because the particle size is smaller. Okay, and our second mark is going to be to do with the collision theory. We're going to say that the collision frequency has increased, so there's a greater chance of a successful collision, and of course that increases our rate of reaction. Okay, that's the end of that question. Nice, quite straightforward question there. You should be able to achieve full marks. Great, thank you.